click on the link called Project Teams Complete, and so the first few teams that have signed up have now been formed up. As people submit their preferred working pair, then I'll run this program again that forms up the team. So there we've got a team of MEng and Comp, a team of SSIT, it turns out, here we are, and so we've got another MSc team, one there. So I think now there can only be 4 more fourth year undergraduates. So whoever are the last 4 in that group will form up the third team of students on Com 4159. And just to remind you, the sign-up form is this one here, and you get to fill in some information about you and your partner. Make sure your partners know who you've chosen. Obviously the program doesn't run if the same person gets included twice as the partner of somebody else. And eventually we should have about 20 teams, I think, in the end. So that's just a reminder. Thank you for those who've signed up and got well organised. You can get started straight away on the project first stage, which is the project pitch here, which explains what the objective is going to be. So it gives you some instructions there, including some things that are going to be delivered in your first stage report at the end of week 6. So you can get started sooner if you like. The first stage is a proof of concept, so you'll read through that, you'll see what it's about. And then the second stage takes that through to the complete implementation. Bit by bit, we're going to be building up your technical skills. We got into programming with Linux on last Friday. Tomorrow we're going to look at basic web programming with CGI programs so that you can have websites that have interactive buttons and produce interactive content. We're coming up to CGI programming in week 3. Then after week 3, we'll get on into using Java servlets and cloud deployment and so on. So I'm awaiting on the support teams to give us the accounts for the cloud platform. I imagine we'll have those by the end of week 3, which is our usual sort of kick-off time. Okay, so we're building up your sort of technical life skills in the Friday labs. Have a look at those to see if you need to learn how to do some of these basic things. And then sort of from about week 4 onwards, I think it's going to be definitely relevant to everybody who's never done that sort of stuff before. But by all means, have a go, work your way through those exercises. You can do them in your own time. I and one RA will be there as a demonstrator to help you through the programming classes on Friday. So today's lecture, the first one this week is all about cloud service models. And then tomorrow's lecture, Friday 9 o'clock, sorry they're very early starts, is the Open Nebula infrastructure, where we'll be explaining what the cloud platform is that you're going to be using here. So that's what's coming up this week. Right. I've got a video embedded in today's lecture at a certain point, so I hope that actually works. I think I've enabled it, but we'll see how this goes. Probably the most relevant source to have a read about cloud service models is this one, Design Decisions for Cloud Computing Service Models, how you decide what sort of offering you're going to provide in the cloud. Out of the said books. Today we're going to unpack those sort of 3 different levels of cloud service models. We're going to look at, say, infrastructure as a service to begin with. For example, Amazon Web Services. We're going to have a look at platform as a service, examples of this being Heroku or the Google App Engine. And we're going to look at software as a service, for example, Salesforce. And we'll look at some other stuff. And then we'll look at the idea of the cloud stack and multiple providers collaborate together within the cloud to produce, sort of increased value offerings. This leads towards something that we call cloud service ecosystems later on. So, cloud service models. We saw a sort of brief introduction to this in the first lecture. And infrastructure as a service, which is kind of shortened to this acronym IaaS, is the lowest sort of entry level of cloud. And you've got a number of good players in there, such as Amazon. If you remember, the reason why Amazon is a massive infrastructure provider, it has to do with the fact that their business was based on initially a bookseller, online bookseller, but then an online retailer of everything, and they needed so much hardware to run their business to cope with Black Friday, the most busy trading day in the annual calendar, that they had a lot of computer hardware lying idle the rest of the year, so they decided, could we make some money out of it by renting it to other people? IBM's infrastructure as a service is called SoftLayer. They have a platform built on top of that, which is called Bluemix. And Rackspace has been going also for some time, not so well known as the others, but is a big provider of data centers and infrastructure to direct to businesses in the USA. We looked at platform as a service, and I guess here in Sheffield we've got quite a linkage with Microsoft Azure now. We have the research software engineering team run by Paul Richmond here, and they have contacts with Microsoft, Azure is taking off as a platform with ready-made collections of apps, simply because users are familiar with Microsoft and the way Microsoft products work. But Azure has all sorts of other exciting things in it now, such as tools for doing machine learning, where you can sort of plug and play together different components to build a kind of training regime to train your either your neural network or your statistical pattern classifier. The Google App Engine has been one of the longer running platforms as a service, which is where you can actually interface with the Google coding technology and provide apps that interface with Google. These two you might not know so much. Zoho is interesting. Heroku is quite good if you're a sort of a hobby programmer. You like to program in all sorts of hobby languages like Python and Ruby and Clojure and other things. It provides lots of programming language interfaces. Zoho, I think I've got an example of building an app later. They provide a sort of toolkit for assembling your own apps in a sort of dynamic way. Then software as a service, this is where you actually rent the end user software. So it's not just a platform with some sort of basic applications on it, but the entire sort of software that you need to use in your business. When the entire thing is provided for you, then we call this software as a service, of which the Salesforce business-related software is the prime example. Although, of course, the entire Google Office application set, which we now use in Sheffield, we use Google Mail, we use Google Calendar, Google Groups, Hangouts, various other things integrated with the university system. So, looking at infrastructure. So, as I come to each of these cloud offerings, we call them, we're going to ask ourselves the question, why should I buy this? Why should I rent that? What's the point if I'm a company of doing that? So why should I buy IaaS, infrastructure as a service? Well, the commercial benefits to me as a company would be, as a small company, I avoid owning or maintaining my own hardware. I don't know how big my company is going to grow, I don't know how much hardware I need, so I avoid buying that up front. Or if I'm a larger company like IBM, the reason for doing this is that it allows me to pool the use of all of the infrastructure that I do own already. So IBM has fewer larger data centers nationally that are in full use. And the way this works is that the hardware that you offer is virtualized. This means that when you think you're talking to hardware, you're not actually talking to the real hardware, but you're talking to a virtual layer on top of the hardware. And this virtual layer then communicates with the underlying hardware. What is interesting is that you don't need to know where the virtual layer physically is. And this virtual layer on top is often known as a hypervisor, so we'll be coming across the term hypervisor in later lectures. And this hypervisor layer can allocate one-to-many virtual machines. So you can sort of spin up a number of virtual servers. We will refer to these as virtual machines. Sometimes they're referred to as instances, because they're instances of your particular server with a particular software image on that server. And you can then upload a complete image of your operating system. So ours will have, Linux on it, it will have Tomcat on it, it will have a MySQL database server on it, and so on. But you could operate, upload, start up a server with a Windows image on it if you're in the sort of Azure world, for example. And the idea is that these servers are elastic. You can allocate more virtual machines, allocate more VMs on demand, and part of the job of the hypervisor is to do load balancing. So it's going to spin up more virtual machines on demand and shut them down when they're not needed, and try and maximize the usage of the physical resource by sharing out virtual machines to different customers. Looking a bit more at what this virtualization layer looks like, what does a virtual machine look like? Well, it looks and feels like a regular server. From the outside point of view, it's just as if you were talking to a real server. But actually what you're talking to is a share or a slice of some other hardware. And the allocation of this hardware, you don't know where it's coming from, so we say it's location agnostic. We don't know where it is physically based, and you access it directly via this layer called the hypervisor. And what sort of resources do you get in your virtual machine? Well, basically the three main things which you buy when you're in the cloud, fundamental things: bandwidth, compute power, and storage. So bandwidth, that has to do with how much you need to occupy data channels, transmitting data to and from different machines. Compute power, that has to do with how many CPUs you need to occupy to perform the computation that you want. And data storage, how much disk space you need to store your data. Each of those three things will be charged by some means. You can have an operating system of your choice on there, Linux or Windows, and software of your choice, such as a regular web server or an app server. And it's typical to upload a sort of prepared software image. So you decide what your preferred collection of software is going to be, then that is what gets loaded up every time you start your virtual machine. Something now a little bit more about the hypervisor, this layer that gives you access to it. What is it? Well, it's kind of like a software layer controlling access to resources. In general, hypervisors exist maybe on your own personal computers now. The system that controls, for example, the download of updates is a secure hypervisor. What it has to do is it has to ensure that the updates that are being installed on your computer are genuine updates that came from your operating system provider, for example, Microsoft. And they control what can and cannot be installed on your machine. But in cloud, a hypervisor is a sort of software layer controlling access to these resources. What it can do is spin up or shut down different virtual machine instances. And the hypervisor offers a sort of guest operating system to the clients who wish to use the cloud. So it appears to you as if it's a regular Linux operating system, or maybe a regular Windows operating system. There are two kinds of hypervisor, and we call them type 1 or type 2. Type 1 are also known as native hypervisors. And these are hypervisors that run on top of bare metal, we say. That's the kind of the raw hardware sitting underneath the software. So they're specially implemented hypervisors that underneath talk directly to the array storage and the processors and so on the hardware. A bare metal or native hypervisor. Examples of this are given below: the Oracle VM Server, Citrix, Zen Server, VMware ESX, and Microsoft Hyper-V. So basically you've got just some virtualized operating system sitting on top, one operating system, and then through there you're talking directly to the physical hardware at the bit level. The second type of hypervisor is called a hosted one, where this sits on top of your host operating system. So in this case, the difference is that you've already got physical hardware, a physical server. That physical server already has its own operating system running it, but then sitting on top of that operating system is a hypervisor layer, which is communicating to your server through its natural operating system. But the hypervisor is offering alternative possibilities of operating system to the clients. So there's a sort of extra layer of software there, an extra sort of level of indirection. Type 1 hypervisors offer a public operating system, but then operations are binary and affect the hardware directly. Type 2 hypervisors sit on top of an existing operating system, so they allow you to interact with themselves as a public operating system, and then they forward commands through to the sort of private operating system of the server underneath. And examples of this include VMware. I know there's at least one student who says, I've got a VMware account in this class, so you know what we're talking about here. Yeah. A VMware account and things like this. VirtualBox is another example of that kind of hypervisor. So that's what a hypervisor is. How does it work? Well, it performs various kinds of scaling activities, and there are two kinds of, or two different dimensions in which scaling of resources can happen. And they're called vertical and horizontal scaling, and we'll try and explain what the difference is between those. So virtual scaling has to do with a share of the resource, the physical resource that you have on a particular piece of hardware. So we talk about scaling up and scaling down. That's in the sort of vertical dimension. Scaling up means you're grabbing more CPU cores from your current hardware, or you're grabbing more RAM space, random access memory, to do your computation. Scale down is where your compute problem requires fewer CPUs or a less RAM, and obviously when you're working on a sort of shared server, you can be sharing some CPUs with you're occupying them some of the time, and then at other times some other person might be using the same CPU. So it's a shared resource. And the scaling up is limited by the maximum resource on that machine. So once you reach the sort of peak number of CPUs installed on this server, that's the maximum you can use. If you wanted to go higher than that, then clearly you'd have to sort of switch off the server, get some more hardware, plug it into the server, then restart your server. So there's a limit to how high you can scale up without sort of switching off the machine and re-provisioning. So then there's this alternative method, which is called horizontal scaling. Whereas vertical has to do with the share of resource that you have on the current hardware, horizontal scaling is all about having multiple virtual machines and spinning up more virtual machines, which could be, of course, linked to different hardware that are somewhere else. And the terminology that's used in the cloud is we say we scale out when we're spooling up more virtual machines from some ready pool of such machines, and we say scale in when we turn off some unused virtual machines, return those existing virtual machines to the pool. And this allows us to scale, far beyond the limits of just one piece of hardware. So this is when people talk about scaling, usually they're mostly thinking about this second kind of scaling, where we're spinning out more virtual machines. And again, the scaling in this case is limited only by the number of virtual machines available. And if you imagine you've got hardware all over the world, you could spin up more and more and more virtual machines. and so therefore you've got a very highly dynamic and responsive arrangement. And in many sort of cloud systems that work this way, you can sometimes say, I have this kind of compute problem. I expect I'm going to need maybe a couple of virtual machines to do my business now. I want to keep another one spare on standby, my sort of hot spare virtual machine that's ready to come online, and then maybe I'll reserve another 5 or something like that, which are now currently shut down, not ready to, not immediately active, and you can arrange a sort of policy with your cloud provider about how you're going to run the various virtual machines that are available to you. So you can have one that's up and running now, a sort of hot spare that's up and ready to go if you need your hypervisor needs to switch some work to it, and then a number of sort of standbys that you would spin up later. You can declare that in advance. Amazon Web Services works like this. The platform that sits on top of that, which is the Elastic Compute Cloud, you can boot 1 to many virtual machines through some simple web interface. And the instances there, they can contain whatever software you desire. And some of the storage services that you can get on Amazon are as follows. The most complex one is called the Relational Data Service, RDS, which is a sort of full relational database capacity. It manages normalized tabular data, and that can sit underneath a number of different proprietary database products sitting in the platform layer. They've also got this thing called S3, Simple Storage Service, which is essentially a file system, simple block storage. You have a file, it's a block of data, you store it here, it finds somewhere to drop that file and stores it for you. And then finally it has another thing called Glacier, which is long life storage, or as we say, cold storage. It's a bit like sticking stuff in the freezer. You're not going to eat it tomorrow, you're going to store it for next week. And Glacier is another kind of storage where it's quite cheap in terms of what they charge you to store and keep stuff long term. It's more expensive if you need to retrieve it more often, if you need to retrieve that data. So Glacier storage would be, for example, the kind of storage used by the big data companies that are generating massive amounts of data, and they're not ready to analyze it all yet, so they put it on ice, as it were, for an amount of time, and then later on, when they're ready to analyze it, they move a chunk of that data out of Glacier into maybe Simple Storage Service, where they then process it. So these are the different kinds of data storage offerings sitting underneath the sort of the infrastructure as a service. So that's infrastructure as a service covered. Now we're going to step up a level to platform as a service and try and get to understand what the difference with infrastructure is. And so we start off asking the same question: why do we want to buy platform as a service? What are the commercial benefits? Well, it's rather like it's if you want to avoid maintaining your own, let's say, Windows platform, like the Sheffield managed desktop or something like that. If you want to avoid maintaining your own managed Windows platform with collections of standard applications that everyone's going to use, but you want to offer the possibility of allowing your end users to put further applications on the platform, that's the sort of thing you want to do. So it's a bit like a Windows desktop or an Apple Mac in tray, the sort of if you think of an Apple tablet, the sort of icon tray you have on the front of that, and you tap one of those and launch an app. It's something like that. And there are 2 particular flavors of platform as a service, which is shortened to this acronym PaaS. 2 flavors of it. The application PaaS is where you're building further applications out of other apps. So you're starting off with a kind of a basic set of apps, and then your intention is to build other things on top of it. But another important one is what's called an integration PaaS, and this is where you are wrapping legacy enterprise resource planning systems, so existing point of sale software in John Lewis's or Debenhams, wrapping them up as platform services, and you're integrating together a variety of different business services, but wrapping them up as apps on a platform so you can integrate them. And the features that you would get on a platform as a service are quite variable, and probably in order of sophistication. So we'll start with the lowest level of sophistication and build up to some, quite high level sophistication. So the first thing is, of course, everything is hosted on the web. So to start with, it's on a platform, therefore we have to access it via the web. The next level of sophistication might be, and it also provides load balancing, so it allows you to run stuff and they can be automatically load balanced, so the apps would spin up new virtual machines behind the scenes. The next level would be, you have some sort of app system development kit. If you look at Heroku, the system development kit on Heroku is quite exciting, quite useful. It allows you to program in a variety of different languages and then connect through with the various other apps through all sorts of APIs in Python, in Java, in Ruby, in Go, in Clojure, in all sorts of languages like that. So having a system development kit is useful if you're building applications out of other applications there. Then next, the sort of reusable services or service components that are on the platform already. This is where you've got, you might say, a fundamental collection of pre-supplied applications on your platform which are going to be useful to any other application that you wish to build on top. An example of this is the single sign-in service. This is where a user comes to the platform and they need to authenticate who they are. And rather than every app having to provide its own login system, the app might just call out to a sort of single sign-in service app, and then that authenticates you as a legitimate user. That then means that it's your account that's being billed for the usage of the platform, and thereafter every other app is sort of metering its usage through the sign-in service that you've used. The next level of sophistication might be a sort of marketing and distribution arrangement, and this is where you have something like the Apple App Store. You've no doubt played with your mobile phones and downloaded apps from the Apple App Store. You may even have paid money for good ones, I don't know. Yeah. The App Store is a kind of regulated market. So Apple has a fairly strict quality control system whereby any software you wish to provide to the App Store has to be vetted in a number of ways. And other providers like, say, Google Play have a much less regulated marketplace where you can just put apps there and say, anyone who uses my app it's at their own risk sort of thing. So having a system of marketing and distribution of your apps, for your platform, that's another level of sophistication. And then finally, having a single point of billing. This is where your platform actually manages the flow of revenues to and from the different providers. So of course the platform themselves wants to earn a small fraction of the revenues that they're charging you because they're providing the platform. But then of course they need to distribute money to all the different providers who have offered the different apps on their platform. So they manage the revenues that are sent to the independent software vendors, ISV, independent software vendor. So again, that's another level of sophistication in a platform as a service. In the project that you're going to be doing, what you're going to be doing is building a platform as a service on top of a supplied infrastructure as a service. And one of the things you're going to do is mimic this idea of billing. We have a virtual currency called the peanut. We called it the peanut just so we can say we're working for peanuts. Then that allows you to simulate how this works. So let's have a look at the different kinds of platform. This was a result of research done by one of my former PhD students, Fotios Konidis. He decided after his big survey of platforms that there were essentially three classes or three different groups of platforms. And the most general kind of platform he called generic open platforms. and they're hard work to use. They offer, for example, a basic operating system, a basic developer kit, some basic storage services. You then have to add what you want, for example, your favorite web server, you know, Jakarta or something, your favorite application server, say Tomcat or JBoss, and then various other applications on top. And examples of this kind of platform, you may have heard of OpenShift. OpenShift is used quite a bit in industry. Cloud Foundry is another one. I think that was the one that was bought by IBM as the basis for their Bluemix platform. Then the next sort of group of these platforms, Fotios classified them as open platforms with a system development kit. And he said these were only moderately difficult to use. And the point about these ones is that they already offer a collection of useful basic services, such as single sign-in, a mail service, message queuing service. A message queue is an application that takes data from one app and passes it on to the next app. A message queuing service acts like a kind of pipeline linking different applications. Maybe a not only SQL style of database, for example. And then there are lots of system development APIs, application programming interfaces, that allow you to create applications in Java, Python, PHP, Go, you know, whatever your currently favorite programming language is. Examples of this include the Google App Engine, so the Google APIs for Java, for Go, and so on. Heroku, as I mentioned, has APIs also in, you know, PHP and Ruby and Python and so on. And the Amazon Elastic Beanstalk is another platform. And then at the top end, you have a class of platform that Fotios called closed virtual desktops. The idea is they're web-based. They don't require any programming skills to use. They allow you to deploy ready-made apps or to build and create your own apps through a system that they provide for construction. So they're much easier to use, but there is this disadvantage that you're locked into that particular vendor. You know, you can only use the app development tools that these platforms offer. Example of this would be Zoho Creator, and I've got a video coming up which I hope works. So you select and deploy ready-made apps using a sort of point-and-click style, and these closed virtual desktops could be web-based, like the other two, or they might be in what we call a rich client virtual desktop environment. So a rich client virtual desktop environment is slightly different. Whereas here, these two kinds of platform, any interaction with the server is making a call via HTTP over the web. The processing is happening out there in the cloud, and the results are coming back. In a rich client virtual desktop, more of the processing is happening on your local computer. So it's more likely that when you connect up, you're downloading lots of JavaScript, and some of that is running parts of the application in the front house, as it were, with a different style of data communication back to the back end. So you see there are these three different kinds. If you're a kind of real programmer and want to build stuff, this middle class of platform is the most useful one to go for. Google App Engine. So here's an example. There's a Google App Engine logo. That's got different APIs for Python, Java, Go, PHP, and any other language that's compatible with a Java virtual machine. So as well as Java compiling down to the JVM bytecode, there are these other new languages such as Groovy and Scala. Scala is a sort of Lisp-like functional language, or Clojure is another pure functional programming language. They compile down to Java-type bytecodes. And then there are Google-style apps that come with the platform already, such as Google Mail, Calendar, Contacts, Google Drive, Google Sites, Google Maps. And you know, it's easier to write sort of automatically scalable apps this way. There's sort of complete integration with Google Accounts, which is you sign in into Google. and there are some sort of restrictions. The range of apps is limited to those supported APIs. There's quite a lot of language APIs. And there's a restriction to use what are called the Java runtime environment whitelist. So applications can only use a subset of Java classes that have been approved for use running an app. And then if you need a relational database, the native database is non-relational. It's called Bigtable, and instead of SQL, it has a query language called GQL. The main difference is it avoids doing a relational join spanning multiple machines. So that's a sort of, that would be cloud-wise a very expensive kind of database operation to have to do a database join between two tables that span multiple machines. So if you want to handle one-to-many or many-to-many relationships, you have to do this via a special kind of reference attribute in the system. So those are the things you have to learn. So there is some quirkiness, if you like, to the Google App Engine and its API, but if you get to use it, you can integrate with all of these Google apps. So imagine building a nice business application that then automatically links to Google Maps and puts up a little pin to show where your business is, and you can run things like that. This is the process of how you would build a Google App Engine app in Java. So in development, you would use Apache's Maven tool to configure your tool or create or manage the project. So Maven is a project management tool that configures various data and XML files and manages the dependencies between your source files, your compiled files, and so on. Then you write a Java servlet to the backend to service the app, so that's the sort of backend business logic. You write maybe some JSP Java server pages, web pages, to collect or solicit user requests. So you build your business logic directly in Java servlets. You build your presentation layer in JSP. You then integrate this with Google Accounts for authentication. And then any app data, you would arrange for it to be saved to the Google Cloud Data Store. Then you build and test your app on your local development server, and finally when you've finished, you deploy the app to the Google App Engine in the cloud. So it's a reasonably involved development process. And this is the kind of thing you end up having to do when you're developing in the cloud. There's the process of local development, and then there's deployment. There's lots of dependencies between different files and different parts of the system, so it's often useful to have some sort of project management tool to manage that. With Google App Engine, there are some sort of portability concerns. There are fears of being locked into the particular style of the vendor, and this is a kind of a current business issue in the cloud. It's the fear of what is known as vendor lock-in. If I go with Amazon, am I stuck forever doing things the Amazon way? Or if I go with Google, am I stuck forever using things in the Google way? Which is why Fotios Gonidis was thinking it would be useful to be able to provide, on an intermediate level style of platform, sufficient tools that would allow people to migrate from one provider to another. Along with the Google App Engine, there's only one other provider that works the same way, and this is something called AppScale. That's an open source provider of a similar thing that is totally compatible with the Google App Engine. And this allows you to deploy Google Apps on any cloud infrastructure, not necessarily Google's own infrastructure. The next couple of slides, I've got some examples of the Heroku platform as a service. The first slide shows a sort of, you might say, a minimal offering, and then the second slide following up shows a more advanced offering where we've got more stuff out there. So we'll click through these little things. So here we've got the component level integration layer, something like GitHub to store the software, Maven to manage the build. Here we've got the sort of a container for the software to execute on with an operating system image, and a CPU. On Heroku, 1 unit of this processing power, they call it a dyno. A dyno, that's just their sort of trade name for 1 unit of compute power. Then over here we've got the possibility of some data stores. You can have Postgres, a relational database, Redis, which is a NoSQL type of flat file data store with a particular kind of searching capability built in. And then you can have various other third-party services that are sort of created to run on top of this platform, for example, for logging, for managing data, and so on. And all of this is linked together with this sort of integrated platform runtime, this sort of layer here. So that's an example of a sort of simple, low use or low consumption application setup. We can access this on any device. So here's my computer and my phone or something which is accessing these resources. Now here we've got a sort of slightly larger setup where we've got more stuff here, such as metrics and data analytics provided. So we're monitoring our usage. Here we've scaled up where we've upgraded our dyno type to a dyno that has more CPUs, or scale out. We've spun out more dynos here, so we've got 3 different virtual machines working. We can have many more data stores, so terabyte scale data stores down here. You can have other apps such as performance monitors, resource schedulers that are sort of managing when you want to put stuff onto different platforms. So that's how platforms work. Finally, we've got the layer software as a service. Why do we want to buy that? Well, it avoids having to buy shrink-wrap software, installing it on our computers, and then the recurrent costs of upgrading to version 2 of the same software, version 3 of the same software. It used to be the case we had to buy the next version of Microsoft Windows every 2 or 3 years and install new disks on our machine. So buying software, renting software like this means you always rent the latest version products on demand as you need them. And the features could be generic packages, such as for mail, calendar, contacts, business packages for managing human resources, this thing called customer relationship management, CRM, very, very important in any business that's selling stuff to people. Accountancy wrappers for banking, taxation, and legacy systems, so that's enterprise resource planning, that's sort of back-end business systems, banking systems, and so on. And then you might have some custom extensions that have been provided already by independent software vendors, sort of who have gone into partnership with your software company, and you get all of that ready-made, ready to run in the cloud. Kinds of service API you might have, service-oriented architecture, protocols. This is a sort of collection of XML standards for transmitting data over the web. There's an XML web service description language, WSDL, which describes the interfaces that the service provides. There's a simple object access protocol, which is a way of describing message data, and all of this is a standard for transmitting data. Popular modern convention is known as REST, which stands for Representational State Transfer, and it uses simple HTTP requests. So we'll have a lecture on HTTP later. It's the way in which the web works by sending requests and responses, get and post, and it uses either JSON, the JavaScript object notation data format, or XML data format. Again, all processing is on the server side. This is medium and modular, but a bit more bespoke. This one's a bit standard, but a bit slower. And then the third way in which service APIs could be offered could be through a vendor-specific rich client API. This is where you have a rich client desktop, so a lot of the software is downloaded when you connect your platform. A lot of it is running on the client side, but then you have a slow data trickle to and from your servers using the AJAX protocol, asynchronous Java and XML. You have some very secure create, retrieve, update, delete system on your backend server, that's handling this data. So this is faster in the sense it's more responsive, but it's less secure. It risks malware penetration on the client. Most people who build rich client systems spend a lot of their time doing penetration testing to make sure that their data services are not being intercepted and corrupted. Salesforce was best known for introducing the CRM sales online dashboard. It used to be just called force.com, but now they've got the Salesforce One platform, and then all of these different ready-made applications that they offer. So, and they may sound to us to be quite similar things, but to people in the business, each of these applications is doing a different kind of job. So you're building customer loyalty, you're creating marketing campaigns, you're connecting partners and customers, you're merging your contact and account data, you're measuring team goals and performance and this sort of thing. So lots and lots of products that go there. Here's an example then of a platform as a service where you build your own software as a service. So
this video will explain how to build your first app in Zoho Creator. The app we'll be building can replace a paper-based visitor sign-in form. Instead of people signing a sheet at the front desk when they visit, we'll collect this information electronically using an app. Here's what we'd want this app to do. Record who is visiting, when, and from where. Then it'll show me all the information about who's visited and allow me to sort and search through it. First, we create an application. We'll make this app from scratch. As you can see, it's also possible to start your app by importing data or using a pre-built app, but we'll cover those in other videos. After you choose how to start, you give your app a name. Let's call it Visitor Registration. Now you see the creator interface. Don't be alarmed. It's actually quite intuitive. On the left, you have buttons to navigate your app. We'll get to those later. On the top are some commonly used links. If you get stuck, click the question mark for help. In the middle is the playground. This is where you actually build your apps. We'll start by creating a visitor sign-in form. We'll name it Visitor Registration, like the name of our app. First, we need to decide what information we want to collect. Let's look at a paper sign-in form for inspiration. This one has entries for people's names, email addresses, who they're visiting, and what company they work for. It also has columns for recording the time they entered and the time they left. We'll take all these entry fields and use them for our app. We want to start by asking for our visitor's name. Because a name is text-based, we'll drag a single line field from the left onto the white sheet. Think of fields like the entry fields on a paper form. They format the information that people enter. The single line field lets users type information into your form. When you drag it onto your form, you'll see the box on the right change to Field Properties. In another video, we'll explain all the settings you see over here. Give your field a name, and you'll see the text on your form update. We also want to collect our visitor's email address. Creator has a pre-made field for this. When you put an email field on a form, it will check to see if your visitors entered their email correctly. Now we want to know who our visitor came to see and what company they work for. Since these responses have to be written out, we'll use single line fields to collect this information. We will rename these fields Person to Visit and Company. Later on, this will make it easy to search for all the visitors we've had from the same company. Finally, we want to know when our visitors came and left. Creator has two built-in fields for this. One lets people select a date, and the other lets them select a date and time. These fields will give them a little calendar button to enter this information. We'll drag two date-time fields over. One of these will be called Time Arrived, and the other will be Time Departed. There you have it. You created your first app. Now that you've built your first app, let's use it. Click the green button in the upper right. When we were building this form, we were in the editing mode, but now we're in the live mode for using our app. When you share it with people, this is how it'll look. To go back and change your app, click on the Edit This Application link in the top right. Let's fill out our brand new form and click Submit. When you're done, click on this link in the navigation bar on top that says Visitor Registration Report. Reports show you all of the responses you collect with your forms. You can search through them or reorganize to easily analyze information. Of course, you can build much more advanced applications in Creator than this one. Some Creator users have built amazing applications. If you are just starting out, we encourage you to watch more of our playlist of Creator demos to learn more.
Okay, to wind up, here's the difference between platform, infrastructure, and software as a service. Or before the cloud existed, you bought packaged software, you provided your own networking, storage, your own servers, your operating system, your middleware, your runtime applications. If you buy infrastructure as a service, this is managed by the cloud, and then you provide all of those things. If you buy a platform as a service, this much is managed by the cloud vendor, and you put this thing on top. If you buy software as a service, you get all of that provided for you in the cloud. So that's really the difference between nothing, infrastructure, platform, and software as a service. I think that's the most useful way of thinking about it. And there are all kinds of different software applications offered at different levels of the cloud stack that are accessed by different kinds of client. And here, for example, Heroku, for example, can sit on top of Amazon Web Services. So you've got a whole collection of different mail services like Postmark, MailChimp, a whole collection of different message queuing services like AMQP, Rabbit, MQ, PubNum, a whole selection of database engines, some of which are relational, some of which are not. And then Amazon provides these basic services, relational data service, simple storage service, Glacier. And of course, if you connect this level with that level, then say Postgres is going to be talking to RDS, Redis and Mongo will be talking to S3, for example. And so you have this amazing sort of explosion of software products owned by multiple people, all working together out there in the cloud. So to summarize, we've covered where infrastructure as a service came out of, what platform as a service is, what software as a service is, and in the future, there's this possibility of anything as a service. What can you imagine you might want to offer as a service? The whole business as a service, like a cloud-run business, or one of the things I'm offering right now is software testing as a service. Anyone who can write me provide a specification, I can give them a sort of a set of Java tests for their specification, for example. And so who knows where this is going to go. So that's all for today's lecture, and tomorrow we'll be looking in particular at the Open Nebula infrastructure that you will be using. Okay, thank you.